All right, so today I'm going to explain to you why you might want to think twice before storing your confidential data on an SSD. And that's because by the end of this talk, I'll show you that once you put data on an SSD, getting it off might be harder than you think. So at the Non-Volatile Systems Lab, we've been doing research on reliably erasing data from solid-state disks. And this is research I've done with my collaborators, Laura Grupp, Fred Spada, and my advisor, Steve Swanson. And what we found was that the state of the art for erasing solid-state disks, both entire disks and single files, was unreliable. And this could lead to a false sense of security. So you could potentially delete a file, and the file could still be left over on the disk without your knowledge. So fortunately, all is not lost, because we've developed a solution that will allow you to delete these files with confidence. So when we're talking about erasing files, we're most concerned about erasing confidential data. And confidential data is data that we don't want, we only want some people to see, and we want to get rid of it at the end of its life. You probably have confidential data on your hard drive or your SSD right now. And that's probably in the form of browser histories or your tax return. Companies have to manage confidential data, and they have to protect it. Otherwise, they might face, legal liabilities or lose company secrets. And governments have to protect information. Otherwise, they might end up with a situation like WikiLeaks. So for the rest of this talk, we're going to talk about how to destroy data at the end of the life on SSDs. And hopefully, that will help you limit access to the people who only to the access to the people who need it. So what we know about erasing drives comes from years and years of research on hard drives. And our colleagues at UCSD have been doing this for years. SSDs, however, are a very different beast. They're flash-based, they don't have any moving parts, and they use a complex controller called an FTL. And the FTL is the reason why we see these sanitization issues, as I'll explain later. So SSDs are becoming very popular. In fact, we're seeing exponential growth, as you can see in this graph, from DRAM exchange. And we're starting to see more and more use in both enterprise and government applications. And you might have left confidential data on an SSD at one point in time. And even if you have deleted it, if you don't know where that SSD is today, you probably don't know who has access to your data, because the data might still be left over on the disk. So current sanitization tools are designed for hard drives. But again, SSDs are very different. So why is it so hard to erase SSDs? It's these differences that make it difficult. So the primary differences from an SSD to a hard drive are that the recovery process to get the raw data off an SSD is cheap. We were able to get the raw data off an SSD for less than $1,000. There's a wide number of manufacturers. There's dozens of SSD manufacturers, and that's a lot of open space for someone to implement their FTL poorly. Also, it's relatively easy to disassemble and reassemble an SSD. You can do this for a very low cost compared to hard drives. To do the same thing on hard drives, it cost us $250,000. We were able to build equipment for less than $1,000. All this could lead to somebody stealing your data overnight. Somebody could potentially take an SSD out of your laptop, pull the chips off, and read the data that you thought you had deleted off of the drive and put it back in, all without your knowledge. So that's pretty scary. So now that I've gone over the differences that might cause an SSD, leftover data on an SSD, now I'm going to talk about some background on what sanitization is. I'll then go over how our lab validated the state of the art for sanitizing solid-state disks and what we found. And finally, I'll go over a solution we've developed for sanitizing disks in terms of single files. So we're going to define sanitization as erasing data so that it's difficult or impossible to recover. And the natural question is, what do I mean by difficult? So for the purposes of this talk, we're going to talk about at the chip. So the reason we're going to choose at the chip is for 3 reasons. We found that there's lots of leftover data at the chip. Second, it's pretty cheap to get to the chip, as we were able to do it for less than $1,000. And third, the next level is so much more complex. It would involve peeling off the chip and peeling off the layers of the chip and reading the individual flash gates with nanoprobes. So we find that because there's lots of leftover data and that it's very cheap to get to this level, this is an important question to address. So now that I've isolated the level we're going to be talking about, let's go over what causes data to be left over on an SSD and not on a hard drive. And in order to do that, I'm going to have to demonstrate to you how writing on an SSD is different from writing on a hard drive. So here's a diagram of writing data to one location on a disk. And we have both the hard drive and the SSD. So for the hard drive, what the hard drive sees is exactly what the operating system sees. So there's a one-to-one correlation between that. For the SSD, however, because of the way that Flash works and how we have to deal with wear leveling, the idiosyncrasies of reading and writing, the SSD will basically write to the first available free location on the SSD. So as you can see already, the view that what's on the SSD is already becoming very different from what the operating system sees. And if I write to that same location again, for the hard drive, the view is the same, so the data is overwritten. But the SSD will write to the next available free location because it has to do these optimizations. And that leaves the blue data that we wrote previously left over as stale data. And so what stale data is basically data that we wrote to the disk sometime in the past, and now we can't access it anymore because we wrote new data, but it's still there. And this might be a confidential document or something, and this leads to problems in erasure, as we'll see later. So lots of the stale data could be left over on a drive after you've used the drive a lot. And in addition, as you might see, there's actually a lot more space on the SSD than the operating system sees for performance reasons. So there's lots of area for the stale data to be left over. So now that I've explained how this stale data could be produced and why it's troublesome, I'm going to explain how our lab was able to test the state of the art and validate whether it was successful in sanitizing data or not. And after that, I'll present what our solution was to sanitizing single files. So now that we've seen that stale data can be produced on an SSD, we want to measure how much of it exactly is left over. And how we're going to do this is, basically, first we're going to construct a fingerprint that's easily identifiable. So this fingerprint has some special identifiers that lets us determine when we wrote it exactly. It's got some unique patterns so we can easily find it again after the FTL has done some transformations to it. And it's got a checksum so we know that we are reading the data back that we wrote and not some other garbage. Okay. Second, we need a way to see more than the operating system sees. So basically, if we read this disk at the operating system level, we're not going to be able to get to the stale data. So we need to get to the flash chips. And how we're going to do that is basically the same way the data thief would do it. Now, what the data thief would do, the data thief would pry off the chips and try to read off of it. And that's exactly what we did. We built this custom hardware platform to extract data off the chips, and we desoldered chips off an SSD after we wrote our fingerprint to it and tried to recover all the data that was on it. And we would determine that the drive is successfully sanitized if we could find no stale data left over. So the drive has failed sanitization if there is stale data left over, and it's succeeded if there's no stale data left over. OK, so now that I've determined how we're going to measure the stale data effect and whether sanitization is successful, I'm going to explain our results in testing what the state of the art is. And as I've said before, there's two ways you can sanitize a disk. The first is to sanitize the whole disk, and that's to erase the whole disk so that there's no data left over. And the other way is to erase individual files, which I'll talk about later. So the two ways you could sanitize a whole disk consist of these built-in commands. So this includes the ATA security erase unit command, and also a command originally written for hard drives back in 1995. There's also some cryptographic techniques, which I'll talk about later. Also, there's a software overwrite, which is embodied in various government standards, which I'll talk about later as well. So built-in commands like ATA security unit basically instruct the controller to erase all user data. And the idea here is that the controller has direct access to the underlying data, and it should know best how to get rid of the data. So we tested these commands, and the first command we tested was an enhanced version of the ATA security erase command. And some of the drives we tested passed or supported it and passed. So basically, we pulled off the chips, and we were able to determine that there was no stale data on these drives. However, the regular version of the command, there was a lot of variation in the results we saw. The most alarming result we saw was that one drive reported success, that the command executed successfully, but all the data was still left over. We were able to mount the file system after we executed the command, and this is really bad. I mean, if you took your drive, ran this command, and trusted it, and just sold your drive to your friend, now your friend has all your confidential data, and if you did it on eBay, it's even worse, right? So this is a really bad result. We don't like this. Okay. Other drives we tested worked only after we reset it a little bit. It's not as bad as the drive that reported success, but we'd like it to work the first time around, right? And other drives did something called a cryptographic scramble, and we couldn't verify whether they were successful or not. So what a cryptographic scramble is basically a drive is actively encrypting data as you write to it. And when you tell it to erase via this command, what it does is it basically erases the key. So erasing the key is very fast. It's a very small key, right? But the problem is that all the encrypted data is still left on the drive. There's a potential for someone to eventually, a few years from now, who knows, crack the code. And there's a possibility that the encryption method was implemented incorrectly in the first place. We've seen in the PS3 that if you use a bad random number generator, bad things happen. So that's a potential problem. So we think that this isn't really sanitization because the data isn't erased. Furthermore, we can't really verify that the key's gone because there might be a copy of the key on the drive, but we have no idea what the key is. So we can't vouch that this drive's actually been erased. Okay, so basically, for this hardware command, there's a wide variety of results among manufacturers. So next, I'm going to talk about the software overwrites. So software override is at the heart of a number of government standards, and basically, according to the National Institute of Standards and Technology, studies today have shown that most of today's media can be effectively cleared by one overwrite. So we wanted to see if we could clear SSDs with just a single overwrite. So how single overwriting works is basically we're going to take what the operating system sees, and we're going to overwrite it with as much random data as we can. So we're going to overwrite the entire logical space of the drive with random data. And as you can see, maybe the first time we do it through, the FTL is going to move stuff around, and we might not get to the stale data. So if we do this a number of times, we might end up with a result like the one on the right, where there's still stale data left over, and hopefully we'll eventually end up with some number of passes at a state where all that's left is the random data we wrote on the drive in the first place. So we wanted to see how many times we'd have to write over the drive in order to make sure all the data is gone. So our experiments showed that 2 passes were usually necessary, but even on the same drive, we needed anywhere between 2 to more than 20 passes. So we found that software override's unreliable. There's no way to really know how many times you need to overwrite a drive in order to get rid of all the data. And hardware commands are the best if they're correctly implemented. But as we saw, there's a wide variety of how hardware commands are implemented from vendor to vendor, ranging from success to complete and utter failure. Okay, so now that I've gone over erasing whole disks, I'm going to turn over to the other part of sanitization, which is getting rid of single files. So single file sanitization is something you want to do when you are erasing single files while leaving other parts of the drive intact. And basically, for example here, we want to get rid of this document here that's red, and we want to leave everything else on the disk there. This might seem like an easy task, but if we overwrite it, it's very different than in a hard drive. So in a hard drive, we can expect that if we overwrite that file, that what the hard drive sees is going to be exactly the same as what the operating system sees. All the data will be gone. But for SSD, what we'll probably expect to happen is that we overwrite those blocks and that the FTL does some kind of mapping to the next available free spot. And that may or may not be the data that we wrote on the drive originally. So if we keep on doing this, as you see, maybe we'll eventually get the file we wanted to get rid of overwritten. But we tested with a 1 gigabyte file, and we tested an armada of government standards and tests. So what you see here is a graph of our tests, and the bars represent different government standards. And these standards specify that you should overwrite the file anywhere between 1 to 35 times. And the height of the bars is basically how much we were able to recover. So even for all of these tests, even the 35 pass one, we were able to recover at least 40 megabytes out of a 1 gigabyte file. So 40 megabytes is a significant amount of data. And some of these standards even resulted in more than 100 megabytes being left over. So it seems that this might not be the way to go. So we tried to modify the standards in order to give them better performance. So we tried to erase all the free space, for example. And the idea behind that is that way maybe we can get to the chunks of stale data. But that didn't really help at all. In fact, we were left with about the same amount of data. So we tried to go even further, and we tried defragmenting the drive. And the idea here is that maybe there's some chunks associated that we would free up by moving files around. And that didn't help either. So it's clear that erasing single files is going to be a difficult task given the current tools that the FTL has. So what we would like is a hardware command that would let us tell the controller to basically erase that stale data. And that brings us to our solution to the problem, the single file sanitization enhancement. And we call our single file sanitization enhancement scrubbing. So scrubbing is an enhancement to the FTL that allows us to sanitize single files. And unfortunately, it's not as easy as it seems. So there's several reasons for this, but in order to tell you, I have to explain to you how Flash works. So Flash is arranged into different areas that we can write to called pages, as we've seen in earlier presentations. And we're going to represent these pages as these squares here. Furthermore, pages are arranged into larger segments that we can actually erase called blocks. Okay? So the problem arises when you have good data and bad data, good data and data you want to actually erase in the same block. So what happens when you do that? You end up getting rid of everything else that was in that block as well. So we don't want to erase everything else. One way to get around it is to copy the good data out of that block into a new block and then run the erase. But the problem with that is it's slow. And if you're doing this with every single write you're doing to the disk, it's going to really hammer your performance. So another thing we can do is we can try overwriting individual pages. So it would be nice if we could just go in there and wipe that out, go in there and overwrite that out, and then our problem is effectively solved. But the problem is that the data sheets, the Flash data sheets say we have to program in order. And they say this for a good reason. There's a problem called program disturb, which basically results in corruption if you don't follow certain guidelines. But our lab has found that it's actually OK to do this as long as you follow specific restrictions. And we're going to call this arbitrary overwrite a scrub. So for low-density, high-reliability SLC memory, we found that there's actually no restrictions with how many times you can do this arbitrary writing. But for MLC memory, we saw something completely different. So for MLC memory, we see that there's actually corruption that occurs, and this corruption varies based on the number of scrubs you do. And so here's a graph of basically the bit error rate and the number of random page programs or scrubs that we've done. And as you can see, the bit error rate increases as the page programs increase. But there's also a safe bit error rate that that most Flash chips have, and we found that basically through experimental testing that we could figure out exactly how many scrubs or random page programs each one of these chips can tolerate before they reach the limit. And we found that the amount varied, but at least we could test see what the scrub budget was. Oh yeah, so the number of scrubs that we can do to a chip, we're going to call the scrub budget, which is the number of times we can scrub. And this scrub budget becomes important later because it has an impact on the performance of our operations. So now that we have a way to scrub out individual pages, we'd like to implement that into a way of sanitizing single files. So in order to sanitize single files with scrub, we had to decide when we're going to do it. So we implemented basically 3 ways of doing it. The first is to basically scrub every single time you write a new file, and we call that immediate scrubbing. There's also a way where you could scrub in the background when you're free. So that's called background scrubbing. And finally, we can do the scrubbing on demand, and that's basically when we're told to. So immediate and background scrubbing are basically ways to automatically scrub stale data from the SSD. So if we implement, with immediate and background scrubbing, you can be guaranteed that the stale data will automatically be removed. And with immediate scrubbing, basically what happens is the write isn't allowed to complete until we're finished scrubbing. And this gives us maximum security. There's also a method called background scrubbing. So this gives us better performance because we are going to allow the write to complete immediately and put the scrubbing into a queue and do this while the drive is idle. And this could provide us good security, but not as good as immediate because if the drive gets shut off in the middle, there's a possibility that there's still going to be data left over. So as you can imagine, this probably will have an impact on performance. And we basically tested our new scrubbing technique on a variety of benchmarks. There's one that simulates a financial workload, a software development workload, et cetera. And basically, what you see in this graph is the bars represent different tests that we ran for a combination of SLC, MLC memory, and for the MLC memory, the number after the MLC is the number of scrubs we're allowed to perform before the chip gets starts getting corruption and we need to do the block copy. And the y-axis is the relative write latency, and that's compared to an FTL that doesn't implement scrub at all. So for SLC memory, basically the performance is almost as good as the FTL that doesn't have scrub. But as you can see with MLC memory, the scrub budget starts becoming a major limitation because when we have no scrub budget, basically what we're doing is we're doing this expensive copy every single time we're writing, and this has a severe impact on performance. But as we increase the number of scrubs, we significantly reduce the latency so that it almost starts to match the FTL that doesn't have any scrub at all. So with 64 scrubs, we're getting pretty close to that performance. So immediate and background scrubbing are basically a way for us to scrub automatically. So there's also scan-based scrubbing, which is what we kind of wanted earlier. It's a built-in command that lets us sanitize individual files. So what scan scrubbing does is it basically goes through the entire disk, and for example, when we tell it to wipe the red file, it'll go through the disk and get rid of each red file and all the stale copies of it, and eventually we'll end up with the empty disk. Sorry. But for MLC memory, we have to manage the scrub budget with copies. So we still have to do this copy thing once we exceed the scrub budget. So we tested scan scrubbing on a variety of workloads, and we found that, again, for SLC memory, we can do this relatively quickly. We tested a 1 gigabyte file, and we found that we could do the SLC scrub in about 2 seconds. But for MLC memory, again, it varied depending on what our scrub budget was. And as the budget increased, basically we see less latency. But even in the worst case, we only saw a maximum of 30 seconds of latency. So we can do the scrub relatively quickly. So basically, scrubbing is a solution that we have for sanitizing single files. The level of sanitization is successful. And there's also an on-demand scan mode that lets you scan on demand if you want. So in conclusion, Sanitizing storage media is essential for data security. If you don't care about it, chances are you'll delete a file and still have the copy left on the disk. We'll need to verify whether sanitization is successful. As we saw, the built-in mechanisms are reliable, but there's a wide variation on the results and the way the manufacturer implements it. So when it's implemented correctly, it's great, but if it's implemented really poorly, you could end up with that disk that said it was good, said it sanitized successfully, but everything was still left over. Also, hard drive techniques don't necessarily work. You can't just overwrite the hard drive and an SSD and expect it to work in the same way as a hard drive. And that leads single file sanitization to become very difficult. Finally, our scrubbing technique allows us to basically sanitize files by modifying the SSD, and allows us to sanitize those files with confidence without the question factor that software overwrite leaves. OK, so thank you. I'm now open to questions.
Nitin Agrawal, NEC Labs. So I had one question on the scrub operation itself.
Okay.
So my understanding of the flash media was that one of the reasons why FTL have to spread out the writes and not allow in-place updates is because each page program causes some disturbance of the neighboring pages.
That's correct.
So you have to spread out. Does the scrub operation?
The scrub operation is very limited. Basically, all we're doing is writing that single page to all zeros. And not only that, so in SLC memory, it works fine. And in MLC memory, yes, there is this corruption effect that we see. But it doesn't grow as fast as you would expect it to.
Do you have a sense of, since in some cases you have to write many times, do you have a sense of what is reasonable and what is?
So,
especially for MLC, it is.
So in MLC, basically, as you can see, it varies from manufacturer to manufacturer. But you can test each chip to determine how many scripts that it can tolerate before you start seeing corruption.
But are these for the same page or for neighboring pages?
I believe, so these are just for, I don't know, actually. So I don't have data on that.
I'm assuming these are for the same page, right?
Right.
But what I'm saying is that the effect is not only limited to the same page, but to neighboring pages. That's my understanding of the media. But I wanted to see if that actually was true, because that would actually make it harder to make a case for scrubbing if that actually causes corruption.
Oh, right. No, we didn't see corruption with adjacent pages with SLC memory. Yeah.
Thanks.
Hi, Keith Smith, NetApp. So I'm assuming that when you scrub an individual file, the interface is actually that somebody's telling you what blocks to scrub, right? You don't have a notion of what's a file, or is your interface? That's
correct. So to simplify the talk, I talked about files.
Yeah, that's fine. So I'm not sure if this is a question or a suggestion for future work, but my observation is that for some file systems, this is going to be problematic because the file systems, when they write new data, don't put it where the old data was. So you can't use this trick to keep track of the stale data. So the question or suggestion is, I'm wondering if you're thinking about how to sort of integrate and solve this problem throughout the stack, so it's not, it works regardless of what your higher layers are doing.
Yeah, so integrating the problem across the stack would be great, but obviously we didn't have the time to modify the file system too. But at least this allows you, if the file system were to keep track of at least which LBAs that file took care of, at least there's now a way that the SSD can get rid of the stale data that's left over.
Two more quick questions. Michael Condit, NetApp. Did you consider using a technique that wouldn't involve, increasing the error rate, such as just standard flash operations of taking a cleanly erased block and copying a block that has pieces of the file to it, but leaving out the pieces of the file?
Right. So basically, you're suggesting to copy the file, or basically doing the block copy every single time you do it.
Yeah,
right.
and then you can just erase the block.
Right. The problem is erase latency is pretty slow compared to write latency, and basically what in the graphs for a scrub budget of 0. That resulted in very high latency because you're doing that copy every single time you're doing it right. So we tried that, and it resulted in a lot of latency, and that's what our scrub operation actually solves.
Peter Desnoyers, Northeastern. So this was very interesting. I'd point out that for a lot less than 1,000, you can actually get the hardware from 1 or 2 websites in Russia. But just looking at the graph here, what was the block size on this? Was this, say, 128 blocks if you have 64 scrubs on a block?
I don't recall what the block size is.
Because at some point, there's no more pages left to scrub.
Right.
But
yeah.
Have you thought at all about any hardware, if you could ask for any hardware support for this, what would it be?
Okay, so, I mean, what would be nice would basically be a way to switch between, basically FTL would implement all 3 of these modes, and you would be able to tell the FTL either I want the drive to be very secure, so basically scrub all the time, or do this background scrubbing, or I only care for certain files, so this scan-based scrubbing would be great. So basically, it would involve some new commands to the FTL.
Okay, thank you.